record. And there we go. So thank you everyone to connect to our OpenMP webinar. So today we have Michael Klemm and Christian Terboven to make the show. And it's going to be on OpenMP optimization and SIMD. So please, Christian, you can go on.
Okay, good morning. Let me just show my screen. And welcome to the third part on our Programming OpenMP webinar for the EUROfusion project. This is the agenda that we have planned for today, and we titled this Optimizations for NUMA and SIMD. And we consider in particular SIMD of high importance because the next two webinar instances will be about GPU programming. And we discussed it earlier this morning. We want to put the focus on SIMD because thinking in a SIMD style or SIMD style thinking is important to understand how to tune for GPUs. So our agenda for today would again be a review of the, we call it the homework assignments. Michael would do that. And then I would start talking about NUMA and continuing with task affinity on NUMA. And then we would cover SIMD. And finally, we would close with MPI and multi-threading. So we figured that user-defined reductions do not fit into the agenda of today because we still have task affinity, we have still task cancellation that we have to finish from the previous webinar. So you have had access to the slides, and our proposal after a brief consideration would be to start with today's agenda and then talk about task cancellation as a tasking optimization strategy towards the end of this meeting, if time permits. If we don't fit it in here, and that could be the case because we value your questions and we think questions are important, then we would finally, or could finally add a sixth webinar where we clean up MISC optimization topics that didn't find their way into this, into the main topics. So unless I hear objections right now, that would mean you're highly interested in in task cutoff strategies. We would start with the agenda as it's shown on the screen here. Not sure if I see your objections here, probably not. Okay, with that, I would hand over to Michael to actually discuss the homework solutions. Michael, okay?
Yes, but I need the beach ball.
Yeah, I'm working on that.
All right.
I'll make you host. You're ready.
Okay. All right. So before we start, are there any questions that we need to answer from last webinar?
If I may, I have a question on the exercise, but I don't know if it is the right moment or not.
Yes, go ahead.
Yeah, actually, I was looking to the merge sort exercise, and I really haven't cached why you're not using the cutoff strategies that are implementing OpenMP, but you're basically using an if condition for limiting the number of tasks generated by the code. So yeah, I don't understand that point. I mean, I thought to find like a final program at one point, but there's not. So maybe if you mind to comment on that.
Okay, I'm gonna talk about the matmul anyway, so probably hold that question until I'm at the example. You probably have a valid point. The only thing that I don't grasp right now is which part of the matmul would have an if to do the cutoff?
It was a question on the merge sort, Michael.
Oh, the merge sort. I'm sorry. Okay. Yes. Christian, you want to tackle that one then?
Yes. So if I understand correctly, you ask why did we use, let's say, a native code if instead of the OpenMP cutoff mechanisms, right?
Yes, exactly.
Yeah, because of limitations in the OpenMP implementation. and to some extent also because of the data environment. So if you put an if clause onto an OpenMP task and the expression evaluates to false, the task is still created but executed immediately. I believe this is close to what I said in the previous webinar. So that means for the if, the task is created and the the data environment is being created. That means, for example, in the Sudoku code example, the board is copied, but that means in particular for private variables, these have to be created and so forth. Yeah? So there's still some overhead. If you do that within the native code, like shown in the third line here, you can eliminate this overhead. It's just faster because you avoid this overhead of the task being created. If the if evaluates to false, you save the overhead of putting it onto a task queue and so forth. So you save a good portion of the overhead of an OpenMP task, but doing it in native code, a native C code, completely eliminates the overhead. Is that a reasonable answer?
Yeah, but at this point, I have another question, because if I do it natively, as you did in the solution, I'm obliged to basically replicate the code, because I have a function MS parallel and a function MS sequential that I have to call whether I'm generating a new task or not. But I'm expecting that if I just using the OpenMP pre-programmed if condition, then I can just have one function that I call in serial if the final condition is satisfied, or in parallel if it's not, right?
Yes, I understand your point. That's correct. So this is a little bit ugly hack because you have to replicate code. Yeah? And this just gives you a slight performance advantage. So if you don't need that, then you can go for the cleaner way and use the if OpenMP if. And they can also tell you that newer OpenMP versions, or with every release, the overhead is being decreased a tiny little bit. So it will work out better in the future. But so if you think, for example, of the sorting algorithm for a small array like 10,000, in many cases, the serial quicksort is not the best possible algorithm. So if you would really like to speed up parallel sorting, you could use quicksort, merge sort, or whatever in the parallel approach, and then use a very fast sequential sort algorithm, which is a different algorithm. And then you wouldn't have to replicate code. So that could be another argument for doing the if in the native code. But your point is valid. In the example, as we have shown it here, you have to replicate code, which is in general not a good idea. There's no perfect solution that gives you both performance and avoids replication.
Okay, perfect. I understand. Thank you.
You're welcome.
All right. Thanks, guys, for covering my first slide. And sorry for the misunderstanding. I really heard matmul instead of merge sort. All right. Anyway, so quicksort is covered, I guess. Similar idea as with merge sort, same code pattern. So, guys, thank you for covering that. All right. The other thing I wanted to pick out, just as kind of an example of what we had as part of the hands-on exercises, is the matmul, where there were two additional versions, matmul tloop and matmul tasks, and I want to pick those two and show you quickly how that can be done. So this is the regular loop nest, and again, the caveat with that example is you shouldn't be doing that. Use your favorite math library instead, better performance and everything. But just as an educational example, how you can use the OpenMP features that we showed, I think it's a good example. All right, if you want to parallelize that loop nest, basically the idea is that you can attach a Pragma OpenMP task loop in front of the I loop. Whether or not you want to have collapse 2 or 3 really depends on how much you want to look into what performance that gives you, but the most basic solution would be this version, where you just add a regular task loop construct and the OpenMP implementation will figure out the rest, like granularity of your tasks and such. Now, the thing is, this now assumes that this matmul underscore tloop function is called from within a parallel loop context already. So the caller of that function has created the parallel region for you, right? And if you look at the remainder code of this example, especially the main function, you will see that this is not the case. So for this example, you would then have to add the parallel region directive to create the parallelism on the device. I'm sorry, on your system, and then we're using single no wait to pick any one of the available threads to start generating the loop tasks. We're using single no wait because in this example we only have like a single parallel region, right, that closes right where also the single would close, so we don't have to have the barrier that is associated with single. And again, the first private up here, that's kind of this tiny performance optimization which we have shown, where we indicate to the compiler that n is not really a shared variable, but it can have a private copy and keep it in the register or something, so that it can figure out that the value of n is never changing. A, B, and C are automatically shared, so that's not a real issue here. So we don't have to really name them. We actually said it would be good programming style to name them, but you know, for the sake of privity, I omitted that. And when you look at how this pattern now parallelizes the loops, you pretty much end up with this kind of strategy. I'm showing a two-dimensional grid for pretty much the access to the C array here, because that's the one that is modified, right? And since we are parallelizing over the I loop here, we are pretty much cutting stripes out of the two-dimensional C array, and we are processing a whole stripe as part of an OpenMP task. If you would add collapse 2, you would probably get a different parallelization strategy, but it would still work. All right. Okay, now for tasking. So what we already did is, when you looked at the example, there was already some tasking preparations applied. So what we already did is we split the innermost loops, the 3 IKJ loops, and we splitted them such that they were already tiled. So we already had additional 3 loops that enumerate all the submatrices, and then the inner loops would then only process one tile or one submatrix and do the multiply on that subblock. And then, you know, through the enumeration, we would cover all of the matrix as we need by the math. And so the way this would be parallelized is you would add pragma OpenMP task first private, you know, enumerating the individual loop blocks and first private on N and BF. So that's the block size or the blocking factor. That's kind of the similar thing that I was already explaining on the previous slide. But now what you will see is, if you analyze the matrix multiply algorithm, you will see that, you know, there are several blocks that are enumerated up here that correspond to the same block when these loops are running down here. So what you need to do is you need to make some precautions to say, well, you know, this task that I'm creating here has an in-out dependency on the C array of that thing here, right? So this is the description of the block that this task is going to work on in terms of reading C and updating that block. And then there's an input dependency for A and B on those, right? So these are the dependencies that you have in this loop down here on the blocks that are enumerated from the blocking loops up there. So if you visualize that, you end up with this, right? So these are the kind of, it's a different matrix size. So just an example here, but pretty much you can pick, you know, a C block like this one at 1024, 0, And then there are three, in this case, three tasks that will update that that block. And this corresponds to a matrix that is like blocked with a factor of, or with 3 blocks in each direction of the C matrix, right? All right. And again, if you want to call that, you know, again, this code now, as it stands on the slides right now, will assume that the matmul task version is called from an active parallel region that is coming from the caller. If that's not the case, again, the same pattern. We do the pragma OpenMP parallel to launch the parallel region. The thing that I miss here, by the way, is up here in front of the parallel directive. There's the computation to actually create the blocking factor and do some asserts, so that it's multiple, that the matrix size is actually a multiple of the blocking factor, but that's omitted here. So, and then we in this case we use pragma OpenMP master, or if you have an OpenMP 5.1 compiler, then you can also use the mask construct. Similar effect now that, you know, we just pick the primary thread of the team to now generate the task. On the previous slides, it was anyone that was picked. Thomas, you raised your hand. Please
You just
unmute and speak up.
So you just mentioned in this example and in the previous example about whether you have to assume that you're calling from a parallel region or
Yes.
not, and then create the parallel within it if not, but not if yes. There's no way of doing this conditionally, right? Of saying if we're in a parallel region, do this, if not, then don't.
Well, the problem is there is a way. So you can, there's an API call that you can call to figure out if you are in a parallel region, and you can even ask OpenMP what nesting level that is. So, you know, if you have parallel region nested in parallel region nested in parallel region, you can ask how deep that nesting is to make a decision based on that. The problem is, once you know, if you have an if in, it's called OpenMP underscore in parallel. So if you put in a if in parallel, the problem is you then know yes or no, I'm in a parallel region, but the problem is you cannot really launch it, because from within the if statement, you cannot really you know, have the opening part of the parallel region and then down here somehow close it, right? So what you would then have to do is you would have matmul task, right? You would then figure out if you are in a parallel region, you would create, you would just call matmul task implementation. You would have to split this loop part into a separate function. That function would only check, am I in a parallel region? If so, then call the implementation function, and if not, create a parallel region and then launch the implementation function. So there's a slight duplication of code that you would have to make. In C++ with templates, you can get rid of it just a little bit, but that's the only way how you can, you know, make this a pure runtime decision to create a new parallel region if there is none at the moment.
Okay, so the
Right.
better design would be naming schemes of functions and conventions rather than trying to do this at runtime.
Yeah, that's one approach. Yes. So there are libraries where you have, like, you know, like we were showing in the, I think the merge sort example and the quicksort examples are one of those, where you have a quicksort underscore sequential, and then you have a quicksort underscore parallel. That's one way. The other way is similar to what you can do, at least in C++ with templates, where you would have like the quicksort algorithm in STL, and then parallel STL has the same symbol or the same function name, and you can then add a additional template argument to it saying, I want to run this in parallel or sequential or SIMDized or whatever, right? Or the other way, as I was sketching, was to follow the in C++ it's Pimple, but there's no pointer involved, so it's a pretty much a bad name here, though. So the other way would be that you actually split that out into an implementation function, and then you know, make this function up here decide if it's a parallel region, if there's an active parallel region, then call the implementation function directly and just forward the request. And if not, then quickly create the parallel region, pick one thread, and then call the implementation function. So that's like a 5-liner to make that decision.
Thanks.
All right, that's all I had to say. Back to you, Chris.
Thanks. So I think you have to pass a host role to me. Thank you. And I share my screen. So I didn't hear any objections. That means we will start discussing NUMA, which stands for non-uniform memory architectures. And this whole discussion is about the topic of memory access in OpenMP, and in particular also locality. So let's start with a very simple example. Let me show you my laser pointer here. You have an array, let me call it A, and assume n is of a reasonable size, so that the array is, let's say, a couple of 100 megabytes in size. You declare the pointer and then you call malloc, and from there on you can work with A. In most cases, or let's say in almost all reasonable cases, first you have to initialize the array A before making use of it. And here we are initializing the array A with a value of 0. Now let's take a look at modern computer architectures. And I have to admit, this is a very simplified diagram or architecture sketch of a current system. What I'm trying to show you here is that we have socket 0 with 2 cores and some caches, and socket 1 with 2 cores and caches. You will notice that I've drawn this memory not as a single block, but instead I've drawn it as 2 blocks. And this is because on modern systems, we do not have, let's say, a single main memory, but with respect to performance, the main or the shared memory in OpenMP is partitioned. The technical reason for that, and I'm not going too much into detail, is that each individual processor has one, or actually multiple, so-called memory controllers. This is a hardware that's responsible to load data from the memory and also to store results into the memory. And that means there's a memory controller on socket 0 that's managing this part of the physical memory. And there's another memory controller on socket 1 that's responsible to manage the other part of the main memory. But still, we have a compute node with a shared memory. And that means cores from this core over here can also access memory over there by going through the system level interconnect. Depending on if it's a Power, an ARM, an Intel, an AMD, or whatever system, these interconnects look different. And they also manage the cache coherence and quite a few other things. So this is a complicated topic. But for the sake of what we are interested in here, it enables all the threads on all the cores to access all the aggregated main memory. But now if we have 2 different, let me call them physical memory locations, where is this data A being actually allocated? That means physically placed. In order to understand that, we have to understand how the operating system works. So when you call malloc, at the end of the day, the operating system only does something like making a mental note that this application sooner or later might use up to this amount of memory, provided or accessible via this address. So remember, you're working with logical memory addresses or virtual memory addresses. So that means A is an address only known or valid within your application. And A with a certain offset and so forth, as long as the offset is within the range that you have been allocated, is a virtual memory address. However, the physical memory is actually limited. So it could be whatever, 16 gigabyte like on this laptop, or 256 gigabyte on a modern compute node. But still, you could ask for, let's say, 100 gigabyte of virtual memory on your laptop, and malloc would in most cases actually return a valid address. But the operating system is responsible to manage the mapping of these virtual addresses, A, to an actual physical location in the main memory, and also to make sure that there's enough physical memory, or that means, if there's more virtual memory requested than physical memory available, the operating system is trying hard to still keep the applications running, but at some point, if the resources are consumed, it will make the application fail. So what's happening here? Here we are initializing A, and the first access goes to A0, I equals 0, and we write to it the value of 0. And only at this point, the operating system actually has to do some real work. So that means it has to come up with a mapping of this physical address A with an offset 0. It's a logical address A with an offset 0 to a physical address, for example, somewhere here or there. And it does so not on a byte per byte range. It does so on so-called pages. That's a granularity. You might have heard of that before. So that means when it establishes this mapping for A at position 0, it allocates or creates a so-called page, which is a block of memory that's accessible via A. And a page has a certain size. So for many years it was 4 kilobytes, but on recent Linux systems, you can also get larger page sizes, like a megabyte or sometimes even larger. And this pretty much depends on your operating system and so forth. But in many cases, it's still 4 kilobytes, and we're not going into too much detail here. So it means for A0, A1, A2, and so forth, you're still working within that page. And at some point, the index exceeds the page size. And that means the next page has to be created, and so forth. So in summary, the malloc only makes or establishes a mental node for this application, that there's a mapping of this virtual address to a set of pages. However, only at the time the value is the data is first initialized, and later on we will call that first touch. That means first touch, the first access to that variables. The operating system establishes this mapping of the logical address to a set of physical pages. Now, how does it decide if A0 should go here or there? It employs the first touch strategy. So that means at the time the first touch happens, I said it before, in the initialization, it will try to place the memory as close as possible to the core, for example, on which the thread or process is running that performs the first touch. So assuming that there's sufficient physical memory still available on this NUMA node, it will put all the pages that represent the array A onto the memory that's closest to this thread. This is a sequential case. And I think I said that the placement of pages comes from the operating system. And that means all what we are going to say here is to some extent operating system dependent, but Linux and Windows behave more or less the same. macOS is slightly different, but that shouldn't be of concern here. So current Linux versions use the so-called first touch placement placement policy by default. You can override that, and we will discuss that later on briefly. So what happens now in the parallel case? Let's assume we have at least as many threads as we have memory partitions, and I sometimes call them NUMA nodes. And we put one thread here, and we put the other thread over there. That means on the other socket in my simple architectural sketch. And we parallelize the initialization. That means thread 0 starts with I equals 0. Thread 1 starts with I equals n divided by 2. By default, we have a static schedule. Again, the operating system will employ the first touch strategy. So that means the page for A0 will be located here, while the page for A n divided by 2 at that index position will be located here. Still assuming that n is large enough so that the array A has to be represented by multiple pages, meaning more than one. And we can exploit that. So let's go back a step and think of why the memory controller has been moved from, let's say, the interconnect or the bus or whatever into the processor. Because If the threads over here running on these cores access their data closest to them, and the threads over there access their data closest to them, we can achieve a higher aggregated memory bandwidth because of locality. Yeah? So the more memory controllers we have, the higher the aggregated memory bandwidth can be. And to some extent, also it reduces the latency. Yeah? And you know, for many scientific technical applications, memory bandwidth is a limiting factor. And this is why modern processors, even in a single socket systems, often exhibit a NUMA architecture, meaning non-uniform memory architecture, because they have 2 or sometimes even 4 memory controllers within a single socket. So why did I call it non-uniform? Where the core over here has a higher bandwidth and lower latency to the memory over here than if it has to access memory via the interconnect that's located over there. So the memory access performance is not uniform, and this is why we have to deal with non-uniform memory access behavior. If we want to optimize performance, we have to spread the data over the memory partitions in our node in order to enable the system to give us a higher aggregated memory bandwidth. Let me show you, admittedly for a very old architecture, what the performance difference might be. I've selected this architecture because it has a nice factor. But let me explain you first. So this is an Intel Westmere system, pretty old. It had 6 cores per socket. It was a 2-core system. It had one memory controller per socket. So that means we had 2 memory partitions. Here I'm running the stream benchmark, which consists of 4 operations: copy, scale, add, and triad. So for example, copy copies the element of vector B into vector A. If you know the size of the vector and if you take the time, you can actually measure the memory bandwidth in here, gigabyte per second, because copying a large vector into the other is a memory bound operation. If we initialize all those vectors in serial, they will reside on a single NUMA node. And with that, we can run with 12 threads, 6 threads over here, the other 6 over there, and we get the memory bandwidth of, let's say, 18 to 19 gigabyte per second. Back then that was reasonable, but it was a factor of 2 away from what the system could deliver. If we initialize the memory in parallel, like what I've shown on my previous slide, where we use 2 or possibly n threads in order to initialize the memory, we can split the arrays A, B, and C over this and that NUMA domain. Again, we are running with 12 threads, but now these 6 threads access the memory part that's allocated over there. And we get a memory bandwidth of, let's say, 40 gigabyte per second. So with every new or additional NUMA node in the system exploited by our program, we can increase the aggregated memory bandwidth that's available to the application. And this is why we have and continue to have NUMA systems. Every additional memory controller gives us additional memory bandwidth. But as you see here, we have to prepare our program to make good use of that. Sometimes you're lucky and things work pretty well out of the box. But in most HPC use cases, you have to parallelize the initialization of your data structures or allocate the data structures accordingly. In my previous example, I was just saying we put the other thread over there, and now we want to understand how this can be achieved. But first, I wanted to point you to 2 tools that can help to understand the architecture of your system. And actually, I should add a 3rd tool to my slide deck here. So if you use Intel's MPI, there's a tool named or a command named CPU info that you can just enter at the command line. And it will give you information about the number of sockets, meaning the packages in Intel terminology, and also the mapping of processor IDs to CPU cores, and also the partitioning of the main memory, like how many gigabytes are close to each individual socket. If you use OpenMP, you will see that HWLog, a library developed at INRIA in Bordeaux, is part of that, and there it provides a couple of tools like HWLog-ls, for example, that gives you sometimes also even a graphical representation of the system topology. Again, giving you information about how many cores you have per socket and how the memory architecture is organized into NUMA nodes or NUMA domains. This is for informational purposes only. There's also NUMA CTL, empty space -- hardware, which is a nice tool also available on most Linux systems, and I should add that to my slide. Again, it will tell you how the memory architecture of the current system looks like. But for OpenMP programs, you should not write, or OpenMP will allow you to write a program not for a single memory architecture in mind, but it provides a couple of features that allow you to exploit different system topologies, hopefully in a performant way. And this is what I'm going to talk about now. So I said we put the other thread over there, and that means we have to bind the threads. That means we have to limit the cores that are available for the execution of a certain thread or a certain subset of the threads in a parallel region. And this is what we refer to as thread binding. However, what is the right binding strategy? That means if you have multiple threads, what is the strategy to decide which threads go where? And in simple terms, there are two different policies. The first would be to put the threads as far apart as possible. So for the case of two threads, you could put them on two different sockets. And this is what I did on my previous slides. When is it a good strategy? Well, it might improve the aggregated memory bandwidth and also the combined cache sizes. So if you have a memory bound application, it might increase performance. At the end of the day, this is just because you're using more hardware. 2 sockets, 2 third-level caches, and 2 or even more memory controllers. However, if you have a lot of fine-grained synchronization, like for example, 2 threads making use of a log variable, then this might be a little bit slower if these 2 threads are on different sockets, because a log variable cannot reside in a shared cache. So then, putting 2 threads close together, this is the other end of the spectrum here, could increase performance. However, then it would decrease performance if you need large caches or high memory bandwidth. So there's no right or wrong. You have to play with it and understand for your application what is the right choice. However, in many cases, it will be the memory bandwidth that's dominating the runtime, or that's limiting the performance of your application. How do we do that in OpenMP? In OpenMP, when we introduced support for thread binding in OpenMP version 4, we decided against making the core IDs or the details of the hardware available or visible to the programmer. We wanted to provide an abstraction, and this is why we introduced the so-called OpenMP places. The OpenMP places are an abstraction of the hardware, and the place consists of 1 or more processors or cores capable of executing OpenMP threads. And you can define the places, more on that on the following slide, and then apply 3 thread affinity policies to actually bind the threads to the places. Indirectly, you bind to the cores, but in OpenMP, you deal with OpenMP places. There are 3 thread affinity policies. The first one is called spread, similar to what I showed on the previous slide. Spread the OpenMP threads evenly among the places in the system, and it partitions the place list, more on that on the following slide. Then there's close, put the OpenMP threads close to the master thread, but place by place. And then there's finally master, which co-locates the OpenMP threads within the team at the same place as on which the master thread is running. So that means you can specify different strategies to come up with the places, and you can specify thread affinity policies, and both is independent of the concrete architecture on which your program is running. So the mapping of places to the cores can be done in most cases by the OpenMP runtime. Let's look into details. Let's assume we have a following machine. So the two green boxes are meant to represent the sockets. These kind of bluish boxes are meant to represent the cores, and the white bubbles are meant to represent hyperthreads. So this is not any architecture that you would find on the market. This is why I've designed it like that. In almost all cases, I would recommend to use the OMP_places environment variable to make the runtime create the so-called place list, which means a list of places to which you can bind, or it will bind, the OpenMP threads. And you can do so by specifying OMP places equals one of these 5 so-called abstract names, and you can do so at the command line before starting a program, similar to specifying the number of threads via OMP_num_threads. There are 5 abstract names, and I try to be brief here. So threads will create one place per logical thread or hyperthread. So that would be 2 times 4 times 4 on this architecture. Yeah? Because we have 8 times 4, 32 logical or hyperthreads on this architecture. Again, the runtime will understand your architecture and create a place list accordingly. The default is cores. Each place corresponds to a single core. In this particular system, that would be 8 places. And when a thread is bound to a place, it can roam freely within this place, but not go somewhere else. So that means a thread that would have been bound to the place number 6 here could be executed by one of the 4 hyperthreads. And in many cases, this is a good choice for HPC applications. Sockets would mean each place corresponds to a single socket. So that means here we would have 2 threads. LL caches would mean each place corresponds to a set of cores that share the last level cache. On most current architectures, there's one last level cache per socket, so that would equivalent to socket, but there are also others where we have a partitioned last level cache within a socket. And then NUMA domains would mean each place corresponds to a set of cores that have the same access to a certain part of the main memory. Access means access performance. So if you have 2 memory controllers per socket, I would guess that the runtime would give you 2 places per socket. Now let's take a look at an example, and admittedly a little bit of an overly complicated example. So here we say OMP places equals cores. I would like to mention that you can also specify the place list by using regular expressions with the logical core IDs, like shown here. So core 0, 1, 2, 3 would go to one place, would form one place. 4, 5, 6, 7 would form the next place, and so forth. Or we could use regular expressions. But I would consider this only of relevant for exploring performance properties of an architecture or benchmarking, not for the standard application use case in production. In my example, I'm using 2 parallel regions, both with 4 threads, num threads 4. On the first, I specify proc bind spread. That means a spread affinity policy will be used, and in the inner parallel region, I specify proc bind close. So let's take a look again at this architecture here. And because we said OMP places equals cores, the 8 cores directly represent the 8 places. If there's a proc bind enable, the thread affinity is enabled by either using the OMP proc bind environment variable or the proc bind clause, the first thread will be bound to place 0. And then we have the spread, this proc bind here at the outer parallel region with 4 threads. And the spread will evenly spread the threads among the places in the system. And I think this picture illustrates what's happening here. But the important point is that spread also partitions the place list again into equal chunks. So that means this thread here will see that the place list within the parallel region consists of only 2 places, while before the initial thread was seeing a place list to consist of 8 places. And why is this useful? Now, these errors are wrong, sorry. So these errors are actually meant to start all here with this yellow bubble. So the idea is that within the place list partition, sorry, by spread, if we start another parallel region, then these inner threads will remain within the partition that has been created by the proc bind, meaning thread affinity policy on the outer parallel region. And then close will put the threads on the two places, because 4 threads do not fit onto 2 places without sharing a place. So this is why we have 2 threads per place, and this will be thread 0 and 1, 2 and 3. So that means neighbor threads are tried to be put onto the same place. Good. So these arrows are meant to actually start here. Yeah. Let me walk you through a few more examples. Again, we have the same machine architecture in mind, and these were questions that have been put into the OpenMP forum, but similar questions have been asked also on Stack Overflow and so forth. So assume we have a parallel region with 2 threads and we want 1 thread per socket. Yeah? Then we need a binding granularity of sockets, OMP places equals sockets. We say pragma OMP parallel num threads 2, because we want to have only 2 threads. And say proc bind spread, so that means we have 1 thread per socket. Second example, now we are asked to use 4 threads, 1 per core, but only on the first socket. Yeah, we say OMP places equals cores, parallel num threads 4, proc bind close. So if the first socket has 4 or more cores, that means it has 4 or more places, then these 4 threads will all remain on the first socket, because they will go to places 0, 1, 2, and 3. If we have more places than threads, we'll first fill up the places before a second thread is being put into each place. If we have only 2 cores per socket, then this example would not work. Then we would have to come up with a different solution. Again, this is a little bit more complicated. Spread a nested loop, first across 2 sockets, then among the cores within each socket, only 1 thread per core. So we say OMP places equals cores. Spread the nested loop with, first across 2 sockets. So we have num threads 2, proc bind spread. And then within the inner parallel region, num threads 4, proc bind close. So this will achieve the binding. And let me also add a remark on when this is useful. So if you have a higher level degree of parallelism in your OpenMP code and then use parallel libraries, for example, then this will also work, because a spread affinity policy partitions the place list. Okay, so that was a theory. Let's look at a few more things that help in practice. On my slides, you see here just for reference, I don't want to talk about. I have a few API calls that actually help you to work with the places. I don't want to go into detail here, because there are better utilities. This is what I used to present when OpenMP 4 has just been released. And now, to understand how the runtime binds our threads to actually physical parts in the machine, we have a nice OpenMP 5 way to do this. We have an additional environment variable, which is called OMP display affinity. And if we set it to true, it will instruct the runtime, meaning the OpenMP runtime, to display, excuse me, to display formatted affinity information whenever that changes. And obviously it changes at the first parallel region. If from then on the affinity information doesn't change anymore, it will remain the same. Otherwise, it will print the information again and again. So this could be an example output. So we have a nesting level of 1. That means how many nested parallel regions are there. Then we get the OpenMP thread IDs, and then we have the thread affinity printed out for each thread. This is an example output with the OMP affinity format environment variable. We can specify how to print the information to the runtime, or we can use the OMP display affinity API call to actually actively print the information from within your program. And this is what you can put into this affinity format environment variable, or as an argument to the previously mentioned API call, the number of teams and the team's ID, the level of nested OpenMP parallel regions, the thread ID and the number of threads within the current parallel region, also the thread information at the previous levels, if we have nested OpenMP, the host name, so if you have your hybrid parallel program being executed on multiple hosts, you can actually add the host name into it, the process identifier, the native thread identifier. So again, this is useful for hybrid use cases, and the thread affinity list. And for example, this is then how it could look like. The capital L is the level. Here we have only one level of OpenMP parallel regions. This is a thread ID, I assume, N, yes. This is the affinity information, and this is a host information. It's a really handy debug utility to understand if the thread binding is being performed in the accepted way as you requested. So let me draw a summary here. What do we learn so far? We can control data placement on NUMA nodes, and we have understood that NUMA, respecting NUMA is important for performance, but there are a few challenges. So what happens if the data access pattern changes over time? So we have to deal with that. And sometimes the OpenMP features do not or cannot address all use cases. So I explained first touch. Let me skip over that here. So sometimes you need for more detailed control, and this is what then you can only achieve with working directly with the operating system. So in Linux, there's NUMA CTL. And for example, you see it here. With NUMA CTL, you can, for example, limit the memory domains, meaning the NUMA nodes available to the program, or you can disable the first touch policy and instead, for example, enable an interleaving. So if you say interleave all, it will physically place the pages allocated by your program round robin over all NUMA nodes in the system. Why is that useful? If you're not sure if your program depends with respect to performance on NUMA or not, you can run your program normally, and then you can run your program with this NUMA CTL and the corresponding flag. And if you see a difference in performance, chances are high that NUMA might be a performance optimization target for your program. So you should look at thread binding and also parallel initialization of the data structures. If you need more control, there are Linux API calls or kernel API calls like move pages that actually allow you to migrate data from one NUMA node to another. I'm not going into detail here. If you want to achieve that, you have to ask the main page on how to make use of that. But be careful with that. You start to make your program depend on a certain memory architecture of a target machine. And this is finally the last few slides on this topic. I would like to give you an outlook onto what OpenMP 5 has introduced and will soon be supported in different OpenMP implementations. So you know that there are allocators, in particular in C++, they are explicit objects, but in C you use malloc and free. And in OpenMP 5, we have introduced allocators to actually make the memory management to become an explicit part of OpenMP. And this is the OpenMP allocator handle, which is a reference to an OpenMP allocator. And it allows you to make use of different kinds of memory that might be available in the target system. So there's an OpenMP allocator environment variable and the corresponding API to work with allocators. OpenMP 5 introduced a set of so-called predefined allocators. And why is that useful? So if you take a look at where HPC systems are going, you will see that some of them already support different kinds of memory. There was an Intel KNL system which had high bandwidth memory. There are more and more systems which support large capacity memory, like non-volatile memory that's also addressable or accessible via malloc and not only a block device and so forth. And there are other kinds of memory that might be optimized for read-only variables, or very low latency memory that might be close to a certain core, for example, and so forth. So OpenMP provides these different kinds of allocators, which allow you to express the needs in terms of different kinds of memory of your application. And then the runtime will map, for example, the high bandwidth memory to what is available in the system. If there is a certain memory kind that has a higher bandwidth than the standard traditional, what you would call main memory, then it will allow you to make use of that. But otherwise, it would map this allocator again to the standard main memory. Similarly, if there's large capacity memory or low latency memory, if that's available, the runtime can put your memory request or can serve your memory request out of the special memory. Otherwise, it will just use the traditional main memory. And you can also, I would also like to introduce OMP alloc and OMP free, that are the routines that work with these allocators. So it's very similar to malloc and free. You put in the size. That means, for example, n, meaning number of elements, times size of the element. And you specify the special OpenMP allocator. And if you then replace the alloc with an OMP alloc or the free with an OMP free, you can make use of different kinds of memory without being forced to use vendor-specific libraries or extensions to the base language. And similarly, with the allocate clause that can go onto any construct with a data sharing clause, you can specify an allocator for the variables that are listed here. For example, with that, you can influence where private variables are actually being allocated. And this will also be a topic of discussion in the next webinar when we start talking about GPU programming. Okay, Michael, I didn't have the opportunity to take a look at the chat. Are there any questions or concerns with respect to NUMA that I should address at this moment?
Not really. There was one question about display affinity, but that has been answered.
Excellent.
So we're covered.
Very good. So with that, then I would skip the rest. All right, for reference and discussion in the context of GPUs, and hand over to you with SIMD, okay?
Okay, SIMD.
And I start monitoring the chat.
Thank you. All right. Just fighting Zoom here. All right. Share. Okay, there we go. All right. So I'm going to talk about SIMD. And let me first make a point why we are covering this, okay? So, you know, if you look at x86 and the SIMD features that have been specified by these processors in the past, you've seen that there was a doubling every once in a while. So starting from SSE with 128 bits to 256 bits in AVX, and then Intel AVX 512 introduced 512-bit wide vectors. So in each cycle, when such an instruction is executed, you can process 2 double precision or 4 single precision variables. And then with the latest instruction set architectures, you can process 8 double precision values or 16 single precision floating point operations in one instruction. And, you know, I'm focusing on floating point here, but pretty much you can make the same argument for short integers, 32-bit integers and 64-bit integers. So there's a similar argument to that. And there's even instructions where you could, in theory, process individual bytes. So in AVX 512, you can actually process 64 bytes at the same time, or 64 characters, if you will. Okay, and you know, Intel and the AMD architectures are just, you know, a particular example here. If you look around in the hardware ecosystem and the processors that are contemporary, you will find that ARM has the scalable vector extensions. which have, at least in some implementations that are on the market right now, also 512 bits, and can go up to 2 kilobits per vector register, which is quite an amazing size of data, or an amount of data that you can hold in a single register. There are others. IBM has it, RISC-V has it. So, you know, it's kind of contemporary, and all modern architectures have kind of SIMD capabilities. Now, what's the deal with it? I mean, this is just regular parallelism, right? Let's dive deeper what these instruction sets can actually do. And again, you know, I'm using x86 as an example, but similar arguments are true for other architectures as well. So the first thing, you know, just standard plain old, embarrassingly parallel application of or usage of a SIMD unit. So you have two sources, you specify an operation. In my example, it's a plus operation, so an addition, and you add up those two sources in an element-matched fashion, and that produces your destination register or your destination result. All right, so that's the easy case. Now let's crank up complexity just slightly. Now we add three sources in the mix. So we have the first two sources are operated on with the first operation. In this case, it's a multiply operation. And then the outcome of that operation is fed into a second operation, in this case, a summation, using a third operand, and that produces now what is typically referred to as a fused multiply add operation, where you fused the multiply instruction and the addition instruction into a single instruction opcode. All right, now here the complexity already starts, because if you do the multiplication and the addition as two separate instructions, you get a different rounding behavior, and so a different result than when you fuse those two instructions and you don't do the rounding between the two operations. All right, so that changes the result already, and typically compilers will not generate those instructions unless you explicitly tell the compiler that the floating point model is relieved to allow this kind of reordering of the instructions. All right. The other complexity that comes in are so-called mask instructions. So here the idea is that there are vector instructions that create what is called a mask register. It's shown here, right? And that mask register contains true and false values. And then you can feed that mask register into an instruction to tell that instruction to only have an effect where the mask register has a true value. Okay, so here the effect of the plus operation is only done where we have a true value. And then depending on the instruction set, you have different ways how you can do that. So here I'm showing as an example that the destination is not overwritten, and it's just the old value in the destination register that is maintained. If there's a false value, there are other instructions where you can actually feed in a third operand that you can use to fill those gaps in the destination register, or, you know, there's tons of opportunities how that can be done. All right, and then there's this topic about swizzling, blending, shuffling, permutations, and you name it. So here the idea is that you have an instruction that doesn't really compute anything, but it pretty much takes a specification in this curly braces here that then describes to the instruction how the data should be moved around as part of this operation. So here, you know, from the source operand with that swizzle mask up here, this is the data rearrangement that is being done, and then the instruction stores that into the destination register. So one particular example how these instructions can be used is when you have complex numbers and you want to do arithmetic on those, you need to separate out the real and the imaginary parts. Then you do the proper math operations on those, and then you have to reconstruct the complex number by merging everything together so that you have the same format as before. And I'm pretty sure that there will be, at the end of my SIMD presentation, there will be a question about this. I kind of sense that in my crystal ball. All right. Okay, so this is some complexity that usually a compiler cannot really handle, and here's the reason why it cannot. So typically, when you have a modern compiler, it has something called auto-vectorization, which is usually part of the general optimization passes that the compiler performs for the loops in your code. And what the compiler does is it has some code analysis that detects code properties that would inhibit SIMD vectorization. So you could think of this as the compiler staring hard and well at your code so that it looks at, what are the what is the data access behavior? Is there anything that when I emit those instructions that I was just showing, that would break the code and make it incorrect? Then if the compiler thinks that the code or has been able to prove that SIMD vectorization will not be harmful, it will apply heuristics to figure out if adding those instructions to the mix will actually improve performance and give you a better or a faster code, right? Now, these are heuristics. So, the compiler vendor will somehow decide on examples, benchmarks, or whatever input data and train those heuristics on those input examples. And then the heuristics may be fitting for your application, or they may not, right? And this is then where you need additional compiler options to, mess around with those heuristics and steer them the direction you wanted, so that the compiler does what you're asking for. All right, and then if everything goes well, so the code analysis says, yep, I can vectorize that code, and the heuristics say, yep, it's beneficial to do so, then the compiler will generate SIMD instructions and emit those vector instructions that I was showing earlier. Here, if you look at Clang LLVM, the typical switch is -f vectorize, and then there's another one, -m prefer vector width, where you can specify what is your preferred vector width for a particular compilation unit. So for instance, if you go back to my earlier slides, if you figure out that AVX is the proper thing to use for your code, then you can put in the right width, like 256, to tell Clang to emit those vector instructions instead of the longer or shorter ones. All right, now the question is, what is this code analysis? And there's a ton of reasons why auto-vectorizers typically fail. And here's just a list. It's not extensive and potentially misses like 1,000 cases where a particular vectorizer fails for a particular snippet of code. But usually the first and foremost are actually data dependencies, where the compiler is not able to prove that there are no harmful data dependencies, and that then basically inhibit SIMD vectorization because the compiler is not sure. And then there's other potential reasons like alignments, function calls in the loop block, too complex control flow, including conditional branches. Mostly looking at the Fortran programmers on this webinar, where I've seen Fortran codes where a loop is like 10,000 lines long. These are the loops where the compiler usually bails out and says, sorry, I can't do anything about this anymore. Mixing data types is always an issue. Like, if you have single precision data and double precision data in the same loop, the compiler has a hard time figuring out how to combine those because they essentially mean different vector width, and it depends on the smartness of the compiler if it recognizes those patterns and can actually do something about it. All right, and then there's a whole bunch of esoteric reasons that are less likely to occur, but could at least in theory hit you. All right, what are data dependencies? So if you have two statements, statement 1, statement 2, then S2 depends on S1 if you have to execute S1 before you can execute S2. And if you reverse that order, you break the correctness of your code. So I have an example down here where statement 1 sets A to be 40, and then statement 2 reads A and needs that value that we just wrote, right? If you turn that around, you likely read an uninitialized value of A or the old value of A, and that likely will break your code, right? So this is generally a dependence. There are now a couple of different ways how you can think about those dependencies and what those statements can actually mean. So there's a control flow dependence if S1 and S2 are defined across the control flow. That means, for instance, you should evaluate the if condition, if an if statement, before you start executing the true or else part, right? Because the if condition basically tells you which part of the if statement to execute. So that has to go first, and that's a control flow dependence, right? Also, you shouldn't be executing instructions from a function before you actually called that function, that kind of stuff, right? Data dependence, I already explained. This is a dependency that is induced by the way the code works on the data. So for instance, here, this first example, or this example on the right-hand side is the same thing. Here, what we do is we set B to be 40, and then we are reading B here, and then we are overwriting B with another value. So now we have a dependence between those two statements where we have to execute that one first so that it sees the correct value. And here, that one has to go after after S1 because it's going to destroy the value of B, right? So these are now flow and end dependency. That's just, you know, forward and backward. But the more important thing is that these dependencies can be carried over between loop iterations. And if that happens, then it's called a so-called loop carry dependency, right? Because the dependence on the data that is processed by the loop is spanning several loop iterations. Here's an example. So what I'm doing here is here A of I is being written in one iteration, and it needs A plus 17, A of A plus I of 17 to update A of I, right? So now we have a dependence that ranges, say, from iteration 0 to iteration 17, because A of 0 and A of 17 are used in the computation, you know, in some other loop iteration, that A plus 17 may be used and overwritten by another iteration, right? There's a simple trick how you can figure out if you have such a loop carry dependency. If you turn the loop around, right, you let it run backwards, or if it's a backward loop, you let it run forward. And if you get different results, then you likely have such a loop carry dependency. All right, and what is also associated with a loop carry dependency is called a distance. So here, since we are processing I and I plus 17 in the same iteration, the distance is 17. It's 17 loop iterations that you have to execute until you hit, until you overwrite the right-hand side by using the same left-hand side. All right, what does it mean in terms of a more visual example, right? So the question now is, can we parallelize such a loop, right? And if I draw in the dependency arrows, you see that there's this dependency of distance 17, and there's multiple of those, right? So from 0, there's a dependency to 17. From loop iteration 1, there's a dependency to 18, and so forth. Now, typically, you cannot parallelize these things, right? Because what happens is, when you parallelize it, the loop distributions, the loop iteration space is cut into, say, 2 halves if you have 2 threads for simplicity. So what happens is, at some point, you will cut between 2 loop iterations and assign the left-hand side to thread 1 and the right-hand side to thread 2, which means that this red arrow, this red line, which separates the 2 loop partitions for each thread, is cutting through those dependency arcs, right? And that usually means that you're getting a race condition, and that means your code is working incorrectly, so you cannot really parallelize it. And I leave this little backdoor except for very specific loop schedules, just because in OpenMP you have enough power as a programmer to actually parallelize these things, but it's really hard and usually has performance issues. So, you know, the general answer is parallelization. No, you can't do it unless you really, really want to go deep into the specific corner cases of the OpenMP specification and want to really make that work. All right, what about vectorization? All right, so the difference between general parallelization and vectorization now is that the vector register has a certain size, right? It holds so and so many double precision or single precision values, right? And I'm showing a vector register of 7 here, so to be completely vendor agnostic. And what happens is, you know, you process the first 7 elements of your loop in a SIMD register, and then for the next iteration, you process the next 7 elements or loop iterations of that loop. And then you process the next 7 elements. And by the time you hit the iterations where you see the effect of your data dependency or your loop carrier dependency, you already processed the starting, the source iterations of your data dependency. So that means, yes, you can vectorize these kind of things, but only if the vector length is shorter than any distance of any dependency. So basically, you take the minimum distance of all your dependencies in your loop, and that is the maximum vector length that you can use to vectorize that code. All right, so you have a little bit more opportunity there because the parallelization is kind of confined into a single vector register that has a finite length. All right, here's now an example what can go wrong in languages like C. So a typical compiler may say to you, this loop is not countable, plus it has assumed dependencies. And what I'm trying here is, you know, I want to be a good software engineer by defining a vector type that contains the data of the vector, and then it has a dimensionality or size of that vector, and I'm, you know, wrapping that in a struct to make sure that I keep that information together. And then I have this element-wise product function, which unpacks the data portion of 2 vectors, multiplies it by with each other in an element-wise fashion, and then stores it back into the data portion of the destination vector, right? And what happens is, so, you know, these are pointers, and by looking at the code, the compiler cannot figure out if by incidence the pointer here somehow overlaps with any of those pointers. So that would mean if I write to the memory through that pointer, I'm accidentally overwriting one of the input values here, right? So, and the compiler is not able to disprove that there is a dependency. It's not able to prove that there is a dependency. So it just assumes that there is one to be on the safe side. And that's why the compiler says assume dependencies. The other thing that can happen is that the compiler says the loop is not countable. And that comes in because we are accessing the loop upper boundary, this A arrow size, via a pointer as well. And so in theory, you know, C is an unsafe language. This pointer could somehow overlap with that thing. And even though it's the one of it is an integer, the other one is a floating point number, it may still, an access to that pointer may destroy that integer. And so the compiler, again, tries to be on the safe side by saying, you know, I don't know if somebody changes size, and I have to tell you that I don't know what the exact loop iteration space of that loop is. If you want to avoid that, by the way, the only true solution is to introduce a temporary variable like UB, assign that thing to UB, and then use UB instead of that pointer expression as the upper bound of your loop. All right. Now, what can you do about this? Right. So this is a long-standing problem. I mean, this didn't just pop up in the last 6 months or so. This is here for pretty much the time when the first vector instructions came up in the vector machines, and so compilers somehow needed help to figure out how to, vectorize these kind of loops. So, you could either use special compiler pragmas that I'm showing here, like, these are the Intel compiler pragmas and Cray compiler pragmas. So you could use pragma vector always to tell the heuristics, hey, it's safe to vectorize it. I expect a performance gain from this vectorization operation. And then you would add pragma ivdep to also ignore assumed data dependencies or assumed loop carry dependencies. Plus the vector always would also override the ones that the compiler has been able to prove, right? Now, the problem with that is you have to trust your compiler to do the right thing, right? Because this here, that part about pragma vector always and ivdep, that's no longer regular C code, right? Because you're using these vendor-specific compiler pragmas. On the other hand, it's also not really OpenMP code anymore, because this pragma OpenMP parallel 4 only applies to the native C portion, or that's as the OpenMP ARB has specified it. So adding those additional pragmas basically makes it a non-C, non-OpenMP code. And so the compiler vendor absolutely had to do the right thing to integrate those both worlds in a way that makes sense and actually works. And as usual, it's hard to do so. The way this was fixed with OpenMP 4 was by introducing a standardized syntax and standardized semantics, how to deal with that situation, at least in OpenMP programs. Okay, so the idea of the SIMD pragmas, and you're seeing the syntax on the slides here, is that we do cut the loops into chunks that fit a SIMD vector register, but we don't parallelize the loop in any way, right? So this is how it looks like. You add it on top of your loop, and you tell the compilers that there are no data dependencies, that, for instance, the floating point operations in terms of a reduction can be reordered in a way, and that you accept that there's a difference in accuracy and the bit representation of the result. And then what the compiler does, it takes your loop chunks and vectorizes that into the SIMD chunks that fit a SIMD vector register. All right, these things here are just for your own reading. Pretty much what happens is that private, first private, and reduction carry similar meaning as with threading, but now they are geared towards SIMD. Safeln, if you go back to me saying that you can vectorize something up to the shortest distance of a dependency, this is where the safeln clause comes in, where you can specify, yep, I have a data dependency in my loop, and I want, I'm telling the compiler, this is the distance of the vector dependency, and you can vectorize up to that amount of elements in a vector register. Linear, you can express a linear value dependency between a variable and the loop iteration space. So here we take the original value of the original x, we add I times the step width that is coming in from the linear clause, and that produces the value of x in iteration I. So this can be used if you have, like, pointer-based iteration loops, so that you can tell the compiler how to reconstruct that pointer at a certain place in the loop execution. Aligned, you can specify that there's a certain data alignment. This is not for correctness, but rather for telling the compiler more about how the data was allocated, so that the compiler can do a better job in producing faster code. And then there's collapse, same meaning as before. There is a work sharing construct that can parallelize and vectorize a loop. This is pretty much by providing pragma OpenMP 4 plus SIMD. That's now the 4 SIMD directive, and that pretty much does what I'm showing here. So what it does is it first cuts the loop into chunks for each of the available threads. So it does the parallelization. And then within a loop chunk assigned to a particular thread, it performs the vectorization operation. And as usual and as required, it does, proper handling should the chunk size not be a multiple of the vector width. It will add a remainder loop, and then for a chunk that doesn't start at a clean vector boundary, it also will provide a p loop if needed, so that a couple of elements are executed and then it switches to a vector loop. All right. Now, the trouble with that is you really need to be careful about what you're asking for. So, if you ask for a schedule with chunk size 5, what will happen that you'll get chunks of 5, and 5 is usually not a good thing for a vector width. So if you have something like AVX2, the code will only execute in the remainder loop, because with AVX2 you have 8 single precision values in a single vector register. And if you go back to something like SSE, which is a 4 wide vector machine for floating point, single precision floating point operations, then you will see that the code is spending one iteration in the vector loop, processing 4 elements, and then it will trigger the remainder loop, processing the last element, the excess element that is coming from this chunk size of 5. There's a way how you can fix that in OpenMP quite easily. What you can do is you can add a so-called schedule modifier in front of the static to say, I want static comma 5, but in context of a SIMD loop. And so what the compiler will do for you, it will take that 5 and it will adjust the 5 so that it actually rounds up to the closest vector width in that range. So for AVX2 and SSE, this will actually turn into a 5. The 5 will turn into an 8, so that 2 vector registers fit a chunk size of 8 in SSE, or a single vector register fits that chunk size. And then you effectively avoid the p loops and the remainder loops and get a slightly better performance. All right. I already said that function calls are troublesome within a loop. And here, at least when it comes to vectorization. And so the question is, how should the compiler deal with such a situation where we want to parallelize that loop down here, but we do have a bunch of function calls that we have to call and go through as part of that loop. Now, for minimum, maximum, sine, cosine, and that kind of stuff coming from the math library, there's a pretty good chance that the compiler will have a SIMD version of those functions. But for something like a Euclidean distance that is programmed by the user, the compiler will likely not have a math function or a function from its runtime library. So what you can do is, in OpenMP, you can actually declare a function to tell the compiler it should create a SIMD version of that function. And this is done by prefixing it with 1 or 2 or more declare SIMD directives. And what happens is, for each of those SIMD directives that you specify, the compiler will generate a version of that function that adheres to that declaration. So what that means in reality is this. All right, so down here, we have the minimum and disksq functions. So what we do is, to make them callable from that SIMD loop context, we declare them to be SIMD functions, right? And what happens is that the compiler, and this is actual x86 assembly code now, it will now turn the float A and float B to be vector registers indicated by ZMM0 and ZMM1. That's the syntax for vector registers on x86. And then the function body becomes a vector instruction to do the minimum computation. Or in the disksq function, you see that there's the vector instructions to process a vector of x elements and a vector of y elements by subtracting them and then multiplying those results and squaring it. And then the return value also becomes a vector register. And down here in the SIMD loop, you can then call these SIMD versions of these functions and execute them. All right, there's a whole bunch of things that you can specify here. So SIMD-len, similar to SAFE-len, you can specify for what kind of SIMD vector register width that function should be generated. By default, all arguments are promoted to be a vector register. So what you can do is you can say uniform for a particular function parameter. And what then happens is that this function argument is then retained as kind of a scalar. In branch and not in branch, I will skip for the sake of time. And then you have linear and aligned with that carry the same meaning as before. All right, now the question is this all worth it? And so, yes, it is. This is a bit dated though, so compiler technology has caught up, but it's still kind of interesting to see that data points. So here the blue is the Intel compiler with auto vectorization normalized to 1. And then you see the red bars are the corresponding benchmarks. And they have been augmented with the proper SIMD instruction directives, so that the compiler was actually generating vector code for those. And you can see that there's drastic speedups that are possible. All right, that's all I had to say. There's a question by Thomas: are Fortran elemental functions equivalent to declare SIMD? Actually, it's pure. So anything that is pure, so it doesn't have side effects like print as, throwing C++ exceptions or the likes, can be made a declare SIMD function. In theory, you are correct in the sense that a smart compiler should be able to figure out that an elemental function called from a SIMD context corresponds to a declare SIMD functions, but most compilers are not smart enough to figure that out, at least for the ones that the programmer declares to be elemental. The ones that are built-ins, it should, or intrinsic functions, the compiler should know that it could call them also as a vector version. All right, Christian, back to you.
And I think we're at the end of the time slot.
Oh no!
Yeah, but so we covered what we wanted to cover from what is really important for the next topic. However, we didn't have the time to discuss hybrid parallelization. So I think we have to discuss with Franz how we could incorporate that. So the options would be to put it into the next webinar, or at a final one, that means a sixth one afterwards, where we focus on hybrid and also cover two tasking topics that we didn't fit into the slots so far. I think if you have feedback, you as listeners, then please let us know. Yeah? Otherwise, we come up with a plan to make up for that.
Sure, thank you very much. Okay, so guys, you can send me your feedback. You have my email, and of course we will set up a webinar according to what you need. Thank you very much, Christian and Michael. As usual, this is a great webinar. This is great information, and I really think everyone is happy with this. So I have to close the webinar because we are short in time. Again, thank you very much. The next one is in April. Give me a sec, the time I found it.
April 21st.
21st, okay. Thank you, as usual, 9 a.m., 10:30 a.m. And video will be released on YouTube channel as usual. Thank you very much, everyone.